Good afternoon. On behalf of Engineers Australia, I'm delighted to welcome you all to our Thought Leaders series, Rehabilitating Landfill Caps with Geosynthetics. My name is Amanda and I'll be your host for today. Firstly, in keeping with our custom, Engineers Australia acknowledges the traditional custodians of the country throughout Australia and recognises their continuing connection to land, waters and community. We pay our respects to them, their cultures, and to elders, past, present and emerging. Before we get started, I'd like to acknowledge that today's webinar is being hosted with Engineers Australia's industry partner Geofabrics. Geofabrics is Australasia's geosynthesis specialist. They help their clients deliver and maintain infrastructure by minimising risk and increasing value through the innovative use of geosynthetic products. Geofabrics have supported the Australasian infrastructure sector on significant projects, from the Victorian level crossing removal to APLNG in Queensland and the Christchurch gondola in New Zealand. On these projects and every project they undertake, they have a singular focus to provide smarter infrastructure solutions. Today, we will hear from two speakers, followed by our live audience Q&A, and I encourage you to send questions through to our speakers via the YouTube chat box. And I'd like to welcome our first speaker, James Mackenzie. James is a Fellow of Engineers Australia and a geo-environmental engineer with more than 2 decades of experience consulting to the landfill industry, primarily as a designer of landfill lining systems. James is constantly involved in the design and construction supervision of landfill capping systems involving multiple geosynthetic components. Please welcome James Mackenzie.
Thank you for the introduction. So yes, my name is James Mackenzie and I'm presenting here today on designing landfill capping systems with geosynthetics. So a quick overview. Geosynthetics use in landfill capping pretty much started around 2000. Before 2000, it was pretty much unseen in Australia, and it's steadily increased to the point now where you really won't see a landfill capping system without some geosynthetics, and in many cases, quite a lot of geosynthetics. So I'm going to an introduction to geosynthetics use specifically in landfill capping applications. I'm going to discuss some of the key elements of designing with geosynthetics and what some of those considerations are. And then I'm going to finish with some case studies. So why geosynthetics? It's because of rainfall. The simplistic aim is to keep water out and landfill gas in. They're the two big aims of a landfill capping system, and geosynthetics are ideally suited to achieving those two goals. Once we keep the rainfall out, we've then got runoff that needs to be managed, and again, geosynthetics are very useful for that application. So why specifically geosynthetics in landfill caps? So some of the advantages, they're a manufactured material. So you've got consistency of performance and consistency of supply. They can be quicker to install. They can reduce costs. And as an example, you look at a geocomposite material compared to a quarried aggregate, without doubt there is big savings to be had any time you can take out a quarried aggregate. And they can create airspace because certainly geosynthetic caps are thinner than comparable earthen caps. Some of the disadvantages, well, they're a manufactured material. So you've got production lead times. Manufacturing can be remote. You can't just go next door and dig up some geosynthetics. Consistency of material. So if one roll has an issue, there's a fair chance you might have a whole batch of rolls with an issue, and you'll need to reject that batch, and then that gets into issues with production lead times and so forth. They can be slower to install. As a rule, they're more weather dependent. So rainfall is not is not the friend of geosynthetics installation. It can increase costs where not designed correctly, and they require specialist lining installers. That's not necessarily a disadvantage, but I just mentioned that. So the top left here, we've got a indicative landfill cap of, say, around 20 years ago. The key aspects there is the inclusion of aggregate drainage layers and a compacted clay liner. You compare it down to the bottom right there, which is a fairly typical cap that I would design now. You can see there's no drainage layer, no aggregate material in there, and the GCL has replaced the clay liner. So the cap on the right has taken out a considerable amount of quarried aggregate material, replaced it with a geosynthetic drainage geocomposite, which is a large cost saving, and the compacted clay has been replaced by a GCL, which may or may not have cost savings, may be cost neutral. But certainly the cap on the right is around 1 metre thinner. So why geosynthetics and why? So we're going to look at the why and which geosynthetics are used. So primary use is as a barrier. And you've got two materials that we commonly use: a geosynthetic clay liner, or a GCL, as a replacement to a traditional compacted clay liner. Now I've got traditional in quotation marks there because that is traditional, and it's now very rare to see clay liner in a cap, and certainly GCL is more commonly used than clay now. Geomembrane, so it's typically a linear low density polyethylene. That's mainly due to regulator prescriptions, and it needn't be. Other flexible geomembranes such as PVC would perform equally well in a landfill cap, in my opinion. And together, GCL and geomembrane as a composite liner is very common with the GCL installed beneath the geomembrane. We have recently seen some use of bituminous geomembranes. However, personally, I have no experience with them, but I do note that there's another geosynthetic that has started to be used in landfill capping. Filtration and separation, the domain of geotextiles, typically non-woven, but can also be woven geotextiles. Their use in caps generally related to drainage of both water and landfill gas. Fantastic product for preventing the migration of fines into more porous materials. Reinforcement, look, not typically a role geosynthetics play in landfill caps, but you will sometimes find some geogrids used, but can also be woven and non-woven geotextiles. Typically, we'll see them when they are used in landfill caps either for subgrade reinforcement, where there's some concern around a particular area of the waste. It might be known to have particular voids in the waste, as opposed to more consistent waste filling in other areas of the site, or at the edges of the landfill caps, where there could be concern around the differential settlement between the waste and the undisturbed ground. Cushioning, it's just exclusively the domain of higher grade non-woven geotextiles to protect the geomembrane. Erosion resistant soil stability, again, non-woven geotextiles, and also a range of erosion specific products such as jute mats, webs and cells. The jute mats, some of them are really only a short-term life, used to prevent soil erosion while vegetation is being established. Materials like the cells can be long-term, permanent, and particularly good on very steep final surfaces. And lastly, drainage, both for water and gas. And this is the domain of geocomposite nets and associated products like strip drains. So now we'll just have a look at some design considerations. So how do we go about designing a landfill cap? Typically we start with the license or permit or approval conditions that will generally prescribe the lining system, or at least the performance that needs to be achieved. And more often than not, particularly with large landfills, that will require some form of a composite lining system. So either compacted clay liner and geomembrane or GCL and geomembrane. The geometry of landfill caps is probably the biggest consideration when designing with geosynthetics, and long and steep slopes present some challenges that need some engineering, and that leads into stability. So the cap, it needs to stay in place. I mean that's obvious, but it can be a challenge. So the steeper and longer the slopes, the more designing, the greater the understanding of designing with geosynthetics is needed. And it's the stability of the geosynthetics themselves and the overlying soils that need to be assured and considered in the design process. So if we just go a bit more further into the stability, the considerations, to start with, we've got the stability of the waste slope itself. Typically looking at 1V, 3H at the steepest. Now, a couple of reasons there. Beyond that, the stability of the waste itself, the global stability could be an issue, but also the lining of a 1V or a slope steeper than that becomes problematic. EPA guidance in Victoria, and I would say most states in Australia, is for the steepest slope to be 1V 5H, which is a good starting point. As I say, steeper than that, it does get harder and trickier. And beyond 1V3H, it's very, very problematic. The stabilities of the geosynthetic lining system. So you need, the driving force here is understanding the critical interface of the system and designing around that. And then the stability of the overlying soils, that's dependent on providing drainage. And as a rule of thumb, slopes steeper than 1V7H, you will need to put a geocomposite or a drainage application in there to relieve pore pressure. And that goes above your barrier system. Exposure, look, it's not a big issue in Australia. I don't know of a lot of landfill caps, if any, that are designed to be left exposed. But if the design does require geosynthetics to be left exposed, even if it's for maybe a matter of months or years only, that does need to be considered, and it's best to cover ASAP. And look, designing for the conditions, one size does not fit all. Elements, and as an example, elements of a design for a very steep lined cap won't necessarily be required or relative to designing over flatter surfaces. Likewise, stormwater measures required in, say, far north Queensland will be unlikely to be a requirement for a design for a landfill located in northwest Victoria, South Australia, or other relatively arid areas. So now have a look at some of the materials, and we'll start with geomembrane because that's probably our most common geosynthetic in a landfill cap. As I said before, linear low density polyethylene. It provides superior mechanical performance to a high density polyethylene, and that's why it's the choice for landfill capping applications, because we do need to be mindful that we're designing around the potential for differential settlement. Its sole use is as a barrier. We design with textured both sides for caps. We don't have a need for any preferential slip surface in a cap like we may do with a sideliner of a cell, so it's just textured both sides every time. They require a well-prepared subgrade if not installed above a GCL, and by that I mean essentially smooth drum rolling. Specialist installer, there is significant installation and pre-installation testing involved. And the geomembranes are 1.5 millimetre thick, maybe a millimetre thick, maybe 2 millimetres thick, but they're in that range, and so they're thin and they're prone to installation damage if care is not taken. Geosynthetic clay liner, I think Anthony might be talking largely about these. They're used as a replacement to compacted clay, and as I said earlier, that well and truly a replacement today. Most commonly used as a composite beneath a geomembrane, however, can be and are employed as a single liner, either as a coated or uncoated product. And that coated product, the coating can be installed coating up or coating down, depending on the needs of the design. Again, requires a well-prepared subgrade to minimise damage. It's quick to install and requires little expertise, but the GCL does need to be covered promptly, and we do not want it becoming hydrated before it's covered and confined. GCLs, they're flexible and they're well suited to capping applications. Geotextiles, pretty much designed exclusively with non-wovens. Lighter grades are used for filtration and separation. Heavier grades are used for cushioning above the geomembrane. Installation, like GCLs, is relatively straightforward. There's little to no installation testing required of geotextiles, but be aware they're very UV sensitive, especially the lighter grades, and so it's best to cover ASAP. Lastly, geocomposites. So these are drainage geonets. They're used above barrier systems to relieve pore pressure saturation in the overlying soils, and they drain away the infiltration. Absolutely required on steeper slopes to prevent instability of soils. You can have a complete coverage, or it can be the use of strip drains. And strip drains are products such as Megaflow, great product for, if you like, underneath the cap, underneath the lining component for landfill gas collection, where they'd replace more traditional aggregate-filled trenches. Practical designing. Just a few points here. Specifying materials. When you're specifying material, generally it's you need to balance specifying the performance of what's needed against an awareness of what can be manufactured, or at least what's commonly available. There may need to be the need to design for a material that's just not commonly available, but be aware, therefore, with lead times around a special run. And laboratory testing can be highly beneficial during the design phase, but may not always be practical, or may not always give results that can be completely relied upon if the sources or properties of materials that will form a component of the design aren't known. So this could be the soils or aggregates where a contractor is to supply them. Typically, if you're designing, it's pre-tender and you won't have 100% certainty on what the full products to be employed will be. So that just needs to be balanced, but lab testing in the design phase can and should be undertaken where possible. Stormwater management, particularly with GCL installation, needs to be considered. if there's some sort of flaw, if you like, in the staging or sequencing of construction, it can lead to GCL becoming what we call prehydrated and ultimately may need to be removed and start again. And certainly lastly, but certainly not least, designs need to be constructible. And in relation specifically to geosynthetics, need to be considering roll lengths, roll widths, access requirements, and how that fits with the plant that's required to install geosynthetics. And while not specifically related to geosynthetics, safety in design. Caps, largely unlike cells, there'll be landfill gas, or you should at least assume there's going to be landfill gas, and therefore don't specify spark testing for testing of your geomembrane, because you may set your geomembrane alight. You may need to consider the possibility that there will be leachate. Steep slopes and geosynthetics, that's often not a great recipe, and so you need to be considering the issues of slips, trips, falls, etc. Landfill cap designs can involve excavation of waste, whether there's been overfilling, and you just, if that's the case, again, need to be aware of what that may result in. For example, the presence of asbestos. Ideally, try and avoid excavation of waste if possible. Okay, well, we'll just look at some case studies now. One's a landfill cap, and one actually strictly isn't, but it's a good example of geosynthetic use in landfills. So the first one is the West Road landfill at Werribee here in Melbourne, in the west of Melbourne. It's a barrier system cap comprising GCL and textured geomembrane. Had geocomposite strip drains underneath the capping system for landfill gas collection. It had a geocomposite drainage net above the liner, complete coverage in this case, so therefore there was no need for cushion geotextile. And the two challenges, it was relatively long, so this is a site that did have 1V 3H slopes, and you can see where all the contours are close together there on the bottom of the page. And it had penetrations. And penetrations is something is generally largely unavoidable with landfill caps. And you can see all those black symbols there on that drawing there, or the landfill gas system penetrations. Here's the same picture again. And so I'll highlight here that designing with geosynthetics on landfill caps with respect to penetrations, they're all a little different, and they can need different details for the design. And this is just a screenshot from one of our design drawings here. We worked around 3 different penetrations. The top left, the turkey's nest penetration we call. All of these involve what we call a boot, prefabricated boot, which, as the name suggests, that's the shape. And with the turkey's nest, it's not possible to get a clamp around that. So we backfill the voids within that multiple penetrations with bentonite to get as best seal as we can. The bottom two, the difference there is really just the diameter of them. The wider diameter leachate sump on the left, and the smaller diameter single landfill gas well on the right. Very similar design detail there. The key there, and the key consideration here, is the understanding that waste will continue to settle post-construction of a cap, and we need that connection to the penetration to be able to slide. We don't want it fixed in place Otherwise, that can lead to the rupturing of the liner. Second and last case study, Anglesey landfill, where we had a reinforced earthen wall to vertically expand the landfill. So this comprised geogrids and a terra mesh facing system, and you can see it in the photo at the top there. The design process, the key issues here were stability assessment of the wall and the specification of the geogrid material. And you can see, again, just a screenshot of one of our design drawings for this role. The geosynthetics, I'll just run you through the geosynthetics that are involved in the bottom section there. They're involved in extension of the existing lining system of the cell. So we've got LLDPE geomembrane, GCL and cushion geotextile, as well as strip drains for leachate collection up that slope, up that 1-in-1 slope. And then the reinforced retaining walls got geogrid at every 500 mils. And as I said, the terra mesh facing on the outside. So plenty of geosynthetics involved. Closing summary. Designing with geosynthetics. So it's not straightforward, and it's definitely not one size fits all. Designers and installers need to be specialists. It can provide significant cost savings, can provide increased certainty with material supply and performance, and it can reduce construction time and can result in unrivaled performance. It's my opinion, a well-designed landfill cap with geosynthetics, the performance of that can't be matched by any other landfill lining system. Thank you for your time. I think Anthony's up next, and then we'll be taking questions at the end.
Thank you, James, for a great presentation. And I'd like to welcome our second and final speaker, Anthony Spiteri. Anthony has spent the last 30 years working in civil engineering, specifically the geosynthetics and recycling industries. Anthony's current role with Geofabrics Australasia includes being involved with stakeholders in the landfill industry, urban and regional councils, major consultants, contractors, landfill owners and operators, as well as government bodies, including Sustainability Victoria and the Environment Protection Authority. Please welcome Anthony Spiteri.
Good afternoon, and thank you for the introduction, and welcome to the second half of the Engineers Australia Rehabilitation of Landfill Caps. So as you heard, my name is Anthony Spiteri. I'm the National Business Development Manager for Waste and Containment at Geofabrics Australasia, based in our Melbourne office. And so welcome today. I'll briefly go through the presentation topics. We'll start with the Victorian EPA BEPM guidelines, move on to the two important design considerations, namely the importance of overlaps and the interface friction or sliding, and then move on to geocomposite drains, practical considerations of designing. Further, the importance of temporary gas barriers and their use. And then we'll finish off with the use of GCCMs in swale drains, as well as our conclusion. So to begin, we'll start with the Victorian EPA BEPM guidelines, and they generally comprise a couple of documents within the BEPM guideline, in particular, siting, design, operation and rehabilitation of landfills. Secondly, it's known as Publication 788.3, published in 2015 and fully authorised by the EPA of Victoria. An integral part of this publication is Appendix E, the guidance on GCL use in landfills, and the three authors, Malik Boaza, John Shears and Kerry Rowe, should all be known to you as experts in this field. Part of the BEPM guideline introduces and defines a GCL as a geosynthetic clay liner as a thin, typically 5 to 10 millimetre, factory manufactured hydraulic or gas barrier comprised of a layer of bentonite supported by geotextiles on either side and or geomembranes, mechanically held together by needling, stitching or chemical adhesives. So the manufacture of our product in Australia uses the needling technique. Some of the key design issues to be considered: firstly, bentonite specification and geotextile configuration. So deciding which particular grade will fit your technical specification. Then we move on to bentonite versus leachate chemical compatibility. This is probably more applicable for baseliners rather than landfill caps. Thirdly, a statement on overlap performance. And then we move on to GCL internal friction stability as well as interface friction stability. And BEPM recommends as a minimum best practice the GRI GCL3. So a typical cap, and this is one I'll describe, which is being used at the West Road landfill facility in Werribee. I'll talk a bit more about that later in the presentation. But starting from the very bottom, we will have our general waste or putrescible waste. On top of that, our landfill gas venting system. The GCL liner is then placed over the top of that. The linear low density polyethylene geomembrane to form the composite liner. Then we have our drainage geocomposite, in this case a trinet with geotextiles laminated to both sides, a 600 millimetre subsoil layer, and then finally overtopped with a 200 millimetre thick topsoil mulch layer. And here's a diagram of exactly what I've just described to show the various profile and the various components within that profile. So what is a geosynthetic clay liner and what does it comprise of? So the top is normally a non-woven staple fibre geotextile. The middle normally comprises a bentonite powder. So properties are fairly important but hard to specify. So you can get a powder bentonite or a granular bentonite, but we use a powdered bentonite. The bottom will normally consist of a woven geotextile with or without a non-woven composite. So depending upon the grade, the composite will normally be with the thicker grades, the X2000 and the X3000, and the woven only will be X800 and the X1000. So the cross sections you see there show a really good picture of the various components, including in the sort of top left, the importance of the needle punched fibres which draw through the product and give it its shear strength. Limitations and differences between the various grades. The important factor here is obviously looking at the interface shear performance, particularly on caps and also on slopes. Chemical compatibility comes into it. We can enhance the GCL with polymer modification, and that's normally known as our pH plus grade, used on slopes and also caps as well if required. Prehydration is normally acceptable for X2000 with the correct technique, by design or by accident. GCLs generally rely on hydration and swelling to perform, and most of this will happen in situ. GCLs in the marketplace are underutilised, and why? There is a general misunderstanding of GCL performance and market perception. So a couple of those include desiccation or drying, the erosion of the bentonite below the primary HDPE, particularly on slopes, chemical compatibility, and the perception of confinement layer cost and time. So as we like to highlight, covering liners is a benefit for longevity for any liner whatsoever. And the graph on the right just gives you a bit of a comparative interface friction performance between two different grades, the X1000 and the X2000 on the clay subgrade, which clearly states that the X2000 has a higher value. So we may have mentioned already the two important design considerations is firstly the composite liner system what will your GCL comprise of? What will your geomembrane comprise of? And secondly, your geocomposite drain. What type, biaxial, triaxial, what grade of geotextile? That can all come out in your design. So a very important factor as part of this design process is the interface friction or sliding. So what you see there is one of our shear boxes we have set up at our grid, and we are able to not only test our own product as we produce it, but we're also able to factor in simulating what can happen on sites. So as you know, a GCL is reinforced by needle punching to force the shear failure outside of the GCL plane. Some of the short-term internal shear strength depends on a couple of factors. One is your normal load, the rate of shear, and also the degree of hydration. Generally speaking, short-term peak internal friction angles are around 30% for GCLs. Meaningful design has to be based on long-term GCL internal shear strength. And finally, post-construction or intermediate loading may be the most critical condition for the base liner slope. So that needs to be taken into consideration. So your role as a designer is to identify the critical interfaces, because it's not just a GCL, it'll be a system. What you need to remember is there is always a minimal tensile strain permitted in the liner. And when I say the liner, I mean the geomembrane. So the designer will advise that. Typically in the industry, we see strain values less than 6% required, seeing more often less than 4%. And that's a fairly important part of some of the piezometric testing that is carried out to simulate a baseliner in a landfill. Okay, so that phenomena is used to calculate and ensure that the minimal tensile strain is kept below the requirement. As part of the design process, it is essential to conduct interface shear testing with site-specific materials on critical interfaces. So you need subgrade material, you need rock or soil that is specifically from the site, and that can be used in conjunction with the proposed geosynthetic components. Another idea is to use a geogrid. It can be installed above the profile, and that helps resist high sliding forces and avoids tension in the liner. Our geosynthetic research, innovation and development sector, which is based on the Gold Coast, affectionately known as the grid, offers site-specific testing, including internal shear and interface friction testing. So now we move on to the importance of overlaps, because GCLs essentially are hydraulic barriers, not just the GCL itself, but also the more important overlap area. So it is important to ask the question, why is a bentonite spec important? So as part of BEPM, a GCL overlap performance statement is normally required. And what you see here, a couple of photos, we have a test rig set up in order to test the durability of the paste that was used. So if you look back 10 or 15 years, when you used one of our GCLs, you had to double apply paste. So there was an undercoat and a top coat that was applied to the longitudinal length, as well as some of the transverse edges on the roll. So we wanted to move to a system where we used a single application of bentonite paste, and we wanted to simulate that in this box test. So you can see quite clearly there the setup, testing both the edge and the end roll overlap performance. What we also need to keep in mind during manufacture of the actual rolls is that 500 millimeters from the edge, extra bentonite powder is added to those areas. So in service, when it's being installed, you have the assurance of extra bentonite powder in those areas. So this is a brief simulation or a depiction of the test. So we had the header tank full of water, we had some stone, we had the GCL set up as you just saw in the previous photo, paste and powder set up. The GCL, of course, the collection bag, all sitting above on the table. So we all know, whilst the hydraulic performance of GCLs is rigorously tested, the performance of the overlap is equally important, but presents additional challenges for hydraulic testing, hence this regime. For containment applications, designers should be confident that the GCL overlap performance is at least equivalent or superior to that of the constituent GCL. So following extensive testing at the grid, the hydraulic performance of the AlcoSeal seaming system is now supported by robust hydraulic test data and research, and we have released these as technical notes. As I just mentioned, the AlcoSeal GCLs feature a longitudinal overlap of our Trugel bentonite powder, which is impregnated into the top non-woven covered geotextile. So these are the results of the test. Now, if we start from the very top, we had our baseline single GCL, and we will simply try to measure the normalized flux of that water passing through the system. After the baseline single GCL, we had an end overlap without powder or paste. And we had three samples of that. Then we had the new paste end overlap involving X1000, 3 of those. And finally, the former technique with the undercoat, top coat of the paste end overlap. So the purpose of the test was to ensure that the new paste end overlap was at least exceeding that of the former paste end overlap. And you can see the results very clearly in the table there. So in summary, if we look at overlap testing, the investigation of overlap performance is certainly very critical in the understanding of the performance of the GCL liner system as a whole. Overlap performance generally stabilizes quickly upon hydration of the GCL in a similar way to the normal GCL shortly after construction. The flow through unpowdered or unpasted joints is substantially higher than when powdered or pasted overlaps are used. So that's a very important point. The one-part paste developed proved to have similar performance to that of the normal GCL. So technically here in Australia, we supply pre-mixed bentonite paste in buckets. The powdered bentonite is identical to the bentonite that is placed within the GCL during manufacture. You shouldn't really rely on paste or powdered paste being mixed on site. Through a factory, it gives you a homogeneous mix, which can then be used consistently across the job. Also, transverse roll joints with the one-part paste is quicker to install on site than previously. And finally, establishing a critical hydraulic design value for performance reliant on bentonite specification. So we've got those technical notes available to you on request. If we move on, and I've mentioned it a couple of times, our grid R&D laboratory based on the Gold Coast, set up about 2010. It's a NATA accredited laboratory and can help develop and deliver the right solution for every project. So we provide on-site support for a number of situations you might be faced with. Firstly, analysis and reporting in according to standards and methods, preparing test reports in accordance to Australian and international standards, and supplying in-field trial research conducted around the world. Secondly, developing customer solutions through product design and development through our own ways and means, as well as looking at particular site-specific design, construction, and installation advice on your project. And thirdly, providing ongoing training and development by conducting technical seminars and workshops, including the one today, and also sponsoring and training engineers via our Geofabrics Academy e-learning hub, which can contribute to CPD hours. So the lab itself has been involved in world-leading R&D projects, in particular with the performance of geosynthetic products. So some of the current examples of our R&D include the UV testing of geotextiles, particularly in baseliners where a separation geotextile is used above the leachate stone and that is exposed to the sun prior to waste being placed on that. PE liners chemical compatibility, particularly in the mining industry. PE liner protection cushion testing. So that's the piezometric cushion testing, which is fully replicated in the lab, including subgrade and leachate stone. GCL liquor compatibility. This is really important for particular leachates and also for mining sites. So we have a bank and a library of well over 30 to 35 landfills in Australia where we've actually tested hydraulic conductivity in our labs based upon that. And a lot of that is ongoing testing, has been ongoing for 10 or 15 years. As you saw previously, we also do shear box or interface friction testing, geocomposite flow testing as part of our MQA requirements for sites. For mining sites, tailings filter clogging testing, and also passive tailings dewatering analysis. So the aim is really to design and feasibility engagement with our clients, the designer, as well as the stakeholder or the asset owner of the landfill. So moving on to geocomposite drains, and you may have seen these in your various involvement in landfill design. So effectively what GCDs do are basically collect and convey liquids and gases. So they're manufactured by bonding a compression-resistant net comprising 2 or 3 ribs and sometimes laminated with geotextiles. So in the case of landfill liners or landfill caps, predominantly always laminated with geotextiles. The G-net component is normally HDPE. So if we look at the stronger triplanar, that normally has 3 ribs, a higher compressive strength than the biplanar, has a thick vertical rib combined with narrow upper and lower ribs, which prevent geotextile intrusion under high loads. And that can have a real effect on some of your flow rates. It's less creep impacted and less effect flows over time, keeping in mind your design life requirements for your job. It's normally a single flow direction, and it's better for cyclic loads, for example, beside roads and under roads. The biplanar, only the 2 ribs, radial flows. It's better for high hydraulic heads, which may be applicable in liners, base liners or slope lining, has a lower compressive strength, a higher elongation, can be creep affected under high loads, hence its usual use in caps. It's better for static loads, and finally has more geotextile intrusion due to the shape of the ribs. So what's the primary function? So drainage above the liner, which is our case at West Road. We want to reduce the hydraulic head on the liner. So if we can reduce the pressure on the holes, we have less leaks. Reclaim water from tailings, 10% better recoveries in the mining industry. It also assists in spreading load on the liners. It has huge benefits on that. It reduces the thermal effects on the liner, so less wrinkling and wind uplift during construction. Can assist or protect from UV short term, and also provides foot traffic protection from wildlife or personnel on site during construction. If you decide to drain below the liner, some of the important functions include quantifying leaks through the liner, especially when you have 2 liners and you place a detection geonet between the 2. It can remove piping and erosion risk, provides data for your EOR, assign ALRs for live monitoring, redirects contaminated leachates, reduces the risk for the asset owner, of course, and provides performance data on the liner. So moving on to limitations, and of course, during your design phase, you will consider the limitations on these, pros and cons, obviously. So your compressive load capacity is an important factor. Low interface shear on slopes versus geomembranes and geotextiles, but we are today concentrating mainly on landfill caps. One of the important characteristics we see in technical specs is the peel strength. So that can vary from state to state, and that is potentially a failure plane, so needs to be considered. Geotextile degradation and intrusion, particularly intrusion in service, can be a factor. Creep, you need to look at that carefully. HDPE resin, whether you look at recycled resin or virgin resin or special types of resin, particularly for mining sites. Biological clogging, the geotextile type, do you get heat set versus needle punched? So we produce mainly needle punched products, so they'll be used in our type of geonets. The geomembrane type, intrusion from whether it's linear low density, HDPE, etc., and product-specific testing is suggested. So that's where the grid can come into play in that situation. This is a typical setup which we can use in the lab, which will measure in-plane flow and transmissivity of the GCD. And we may have mentioned some of these previously, but some of the variables in testing will include geonet aperture size and geotextile intrusion. Compressive strength is a variable. Do you choose biplanar or triplanar? The hydraulic gradient can vary between 0.1 and 1. GRI certainly at the moment specifies a 480 kPa pressure that's required for the test. We need to look at whether 50 to 80 kPa is more realistic for caps. Will that save you money and effort on finding and looking at a cheaper alternative for the GCDs that will be fit for purpose? Boundary conditions can vary, hard and soft, and the seating time. You can go from 15 minutes with hard boundary conditions all the way up to 100 hours with soft boundary conditions. And the influence of liquid temperature is rare. So looking at realistic testing patients, this was one of the tests we conducted, realistic test, probably going back 7 or 8 years now, at an Australian landfill directly for our client. And they wanted to look at the test as a system pretty much and looking at the intrusion factors. What are the different intrusion factors based upon whether you choose biplanar or triplanar type geonets? So this cross-section consisted of the primary liner, a 1.5 mil HDPE. The secondary liner was the AlcoSeal X1000. And then further below that, we had an erosion and cushion protection with the Bitum A14. The groundwater or gas drainage geonet, which was the triplanar T5, a 5mm thickness. Underneath that, a subgrade erosion protection Bitum A14, which effectively sandwiched the T5 triplanar. And finally, we used soft and hard rubber subgrade to replicate intrusion. So a number of these tests were carried out for the client, which then allowed us to decide on which particular GCD we would choose, which would be perfect for the job. So in concluding with GCDs, I'll move on to the use of temporary gas barriers and one of the projects that we are looking at next year. So I did mention the West Road Refuse Facility in Werribee, which has been operating since the early 1980s, and I believe has a licence till about 2050. So over the last 12 months, the cell for CAP itself involves a 200,000 square metre composite liner to CAP, and further work next year will involve a temporary gas barrier for the CAP design. And this will consist of essentially a geocomposite liner. It's a 0.5mm polyethylene liner, which is sandwiched between 2 layers of a mid-range non-woven geotextile. So that prepared product is produced in our Albury factory, where the 2 non-woven geotextiles are laminated to the PE liner. So as I mentioned, the site is fully owned and operated by the Wyndham City Council, and the purpose of the temporary gas barrier is to trap and extract methane gas being emitted from the cell. the gas can be extracted and piped to council's electrical generation plant on site. Council already have existing infrastructure, which consists of landfill gas extraction wells, gas manifolds, leachate sumps, and associated pipe infrastructure. So the works involve the construction of this cap along the western waste batter of cells 4A, 4B, and 4C. And as I mentioned before, it will comprise that geocomposite liner and a stormwater management infrastructure. So the whole idea of producing a temporary gas barrier is adjacent to this cell. Cell 7 will be constructed throughout 2024. That will then effectively be filled with waste and eventually reach the level of this temporary gas barrier and then bury it. So it's simply for use prior to the levels of cell 7 reaching that area. Another factor and final factor in what we do in relation to landfills is the use of GCCMs. So if you haven't come across these before, essentially what they are geosynthetic cementitious composite mats that can replace in situ concrete. So in the context of landfills, they can be used to protect drainage channels. So we have a wealth of information on this product that we can share with you, but the picture simply depicts the use of or the installation of this product using a laydown frame. So the product, as you can see there are various applications, including channel lining, slope protection, bund lining in tank farms, and also weed suppression. So we are starting to see the use of this product as known as concrete canvas. It's manufactured in the UK and imported into Australia. So as far as the channel lining is concerned, as you saw from the photo, you could rapidly unroll these rolls to form the channel lining. It's significantly faster, easier and less expensive to install than conventional concrete channels and requires no specialist equipment apart from the laydown frame. The matting can be laid at a rate of around about 200 square metres per hour on a 3-man team or 3-person team. The last product I wanted to briefly introduce to you was our SorbSeal product, known as our hybrid GCL. So this, our grid and Geofabrics worked on over the last 5 years. So it's an Australian-made HGCL. It works as a barrier to liquids and helps trap a wide range of contaminants, including potentially dangerous PFAS, preventing them from entering the surrounding environment. So the product's been modified from our standard AlcoSeal to include a very specific high surface area powdered activated carbon. So that is physically mixed into or mixed with the powdered bentonite during the manufacturing process. And as you can see from the photo, gives it that distinct black look due to the carbon. So it can be utilised in base liners, caps, and specifically leachate ponds where you may experience a higher level or higher concentration of PFAS. So this is yet another example of the development work over several years of our grid. And as you may know, the SorbSeal is now available to the Australian market. So the Geofabrics difference, Geofabrics has been around since 1978, and we opened our Albury factory to manufacture the Bidham geotextile in 1987. So our business is underpinned by our 3 factors here. Australian manufacturing. We firmly and strongly believe in the fact that we are a local or Australia's only local manufacturer of geosynthetics. So we push that very hard with designers, with stakeholders to support Australian made. It gives us a number of advantages. You are dealing directly with a manufacturer, greater quality control, a more reliable supply chain, shorter lead times, and flexibility and responsiveness. When we look at sustainability and innovation, some of our Bidham geotextiles are now manufactured with recycled PET water bottles. To date, we've recycled successfully well over 60 million bottles instead of those ending up in landfill. And there's another lot of innovative products that we are developing in this space. And thirdly, technical leadership, looking particularly at our field service with our engineers, as well as our grid on the Gold Coast, looking at innovation, industry education through our Geofabrics Academy, and finally design and independent testing services through our various labs that we have around the country. So in conclusion, I'd like to just finish off by mentioning some of the points we looked at throughout the presentation. We obviously started with the Victorian EPA BEPM guidelines, best practice capping systems. We then moved into the chief design considerations for GCLs, in particular the importance of overlaps and the interface friction sliding. And finally looked at geocomposite drains, the practical considerations of designing, in particular looking at the realistic testing considerations, and also some typical case studies that we are currently looking at. So that concludes my presentation today. I'd like to thank you for your attention and your attendance, and please feel free to locate us in any of our Australian offices. So thank you.
Hi, thank you so much for our speakers for those two great presentations. As always, it's now your turn to get involved. If you'd like to ask our speakers a question, if you could do so by putting that into the YouTube chat box. And I want to thank everyone also who submitted questions whilst registering, and we might start with some of those. And Anthony, just starting with you, we had a question that came in from Napthali, who's located somewhere in Australasia, asking, Anthony, how can engineers in PNG be able to work collaboratively with other international engineers, especially from Australia, sharing emerging technologies and skills? Anthony, your thoughts?
So firstly, thank you very much for your question. Look, I've got a couple of ideas here. Certainly building links with geosynthetic manufacturers is the first idea. Certainly making sure you're registered for updates from Geofabrics, as well as our Geofabrics Academy. And thirdly, keeping in touch with our Geofabrics New Zealand business, which effectively is responsible for PNG. And finally, looking at Engineers Australia, keeping up your membership and also keeping an eye on these thought series. We normally produce a few of these per year, so that's just some of the ideas that that you can look at.
Thanks, Anthony. Thank you for that. We've got a question that's coming from Ahmad, and Ahmad is watching from the Middle East, asking you, James, and then also asking you, Anthony, what is the biggest material used to cover landfill? Thanks for that question, Ahmad. James.
What's the best material? Well, it isn't any, as I say, one size fits all. But if we want to look at, say, geomembranes, for example, a linear low or any flexible geomembrane will be a better material than a high-density polyethylene. And Ahmed, so in the Middle East, so very hot conditions, again, you might want to be looking at a white geomembrane because there's a lot of advantages with installation with a white geomembrane as opposed to traditional black geomembranes. Good question, though. Thanks.
Anthony, do you have a view on the best material to cover landfill?
Yeah, certainly. Just to add to James's comments in relation to the GCLs, we generally find the grade of our GCLs that have a high tensile strength, and that would normally be the X2000 that is used both on slopes and landfill caps, so that it allows you the flexibility to use that particular grade based upon those properties.
Thank you for that. And James, we've had a question that's come in from Gayantha, who's watching from New South Wales. Good afternoon to you. Putting the question to you, James, first, and then Anthony, asking, is the process similar to phytocapping?
So My presentation very much was talking around barrier system caps. So, if you like, the exact opposite of phyto capping. But even with phyto caps, it would still be relatively common for some geosynthetics to be involved. I would expect you'd have some non-woven geotextiles and some stormwater drainage products involved. But yeah, my presentation very much on geosynthetics in a barrier system cap. So, if you like, the complete opposite to a phyto cap.
Thank you for that. Anthony, do you have a view?
Certainly, I agree with James. Most of our business is involved in barrier systems, so geosynthetics in general. So yeah, we don't certainly have any experience with phyto caps, but yeah, it is almost an opposite to what you would use as a geosynthetic barrier system.
Thank you. And thank you, James. We've had a question come in from Cody, and Cody's watching from Queensland, asking you, James, what is your opinion on the growing scarcity of quality clay for bulk earthworks and alternatives such as bitumen geomembrane? James.
Yeah, so we also see good quality clays for clay liner construction not as readily available as it once was for whatever reason, and the replacement for a clay liner is a GCL. Bituminous geomembranes, as I said in my presentation, I haven't got any experience designing with them. Now, do a lot of my designing in Victoria, and as I said, it's very prescriptive designing, and currently you'd be very hard pressed to get a EPA licensed landfill capped in Victoria using a bituminous geomembrane. I think the industry is still learning about bituminous geomembranes and how they perform in the field, and certainly if you were to design with them, as per some of the comments in my presentation, laboratory testing, understanding the properties of them, particularly strengths, how temperature affects them, and then what slopes and what interface frictions they can achieve would be highly recommended.
Thank you for that. And just staying with you, James, just sort of expanding on what you've just been talking about. And we've had a question come in asking you, James, you talk about stability issues with landfill caps, but are there actually any examples of the potential failures you allude to occurring in Australia? Thanks, James.
Yeah, look, there aren't a lot, but because I think generally in Australia we've got a very good design community, but it does occur, and I am sort of involved in looking at one at the moment in Queensland where the liner the liner ruptured and torn, and the cap failed. So it is rare, but it does happen.
Thank you for that response. And Anthony, just bringing you back in, we've had a question coming in asking, why is it important to consider a composite liner system, geomembrane GCL, rather than a single liner? Anthony.
So Amanda, the composite liner is designed to work specifically as a system. No liner is totally impermeable. They all have a hydraulic conductivity value greater than 0. So ideally, if the polyethylene liner has any pinholes present, the underlying hydrated GCL will act as a barrier to minimise leakage. So that's the key behind using a composite liner system.
Thank you for that. And Anthony, you did discuss the testing carried out on the overlap areas of a GCL. Could you explain why this is so important? Thank you.
Well, certainly for the designers out there, for containment applications, designers want to be confident that the GCL overlap performance will be equivalent or even superior to that of the constituent GCL. So the AlcoSeal GCLs feature a longitudinal overlap with the Trugel bentonite powder impregnated into the top of it. The top non-woven cover of the geotextile. And secondly, the Victorian BEPM guidelines call for details regarding the installation of GCLs, covering overlap orientation, overlap preparation, and also overlap methods. So it's fairly important that you can cover those requirements as part of the BEPM system.
Thank you for that. And I just wondered, we talked about the Thought Leaders series and encouraging our members to get involved. Obviously, this is a field that's rapidly changing. What advice, starting with you, Anthony, would you give to young engineers that are entering this field? Thank you.
Well, certainly young engineers entering the field would certainly keep in touch with Engineers Australia, keep their membership up, which is also important, but also to liaise and network, not just with their fellow engineers that they work with, but also different associations that are out there, and keep in touch with practitioners and also specifiers and also geosynthetic suppliers, just to keep abreast of what changes are happening, because certainly in the 30 years I've been involved in geosynthetics, projects have been, or products have been developed and are now well used in the marketplace, as James had spoken about GCLs not really being used up until about the year 2000. So it is really important to liaise and network with your fellow engineers.
Thank you. James, your advice?
Oh, sorry, just having a few. Sorry, having a few technical issues.
Technical issues.
Sorry, Amanda.
You've navigated them well.
Yeah, I won't be quite answering it directly, but designing with geosynthetics, it is a specialist role, and there are communities out there, particularly the geosynthetics chapter, which has or society, which has a chapter in Australia. That's the one to get involved with.
Thank you for that. Today we are running out of time, and we have covered a lot on rehabilitating landfill caps with geosynthetics. I just wondered if you could give our audience sort of 5 key takeouts on your presentation, and maybe starting with you, James.
Sure. I might be repeating myself a little bit, but it's one size doesn't fit all. Where possible, conduct laboratory testing as part of the design process. 3, look at the opportunities to replace traditional products with geosynthetics. There can be economic benefits involved. 4, for designers and particularly caps, ensure the system is stable. And 5, when specifying materials, but be mindful of what's achievable for the manufacturers, what the site actually needs. There's both issues with over and under specifying, and be mindful of lead times.
Thank you for that. Anthony, your key takeouts?
Sure. Certainly looking at lab testing is the first one I'd certainly emphasise to assist you with designing either your liner or your cap, and using specialist labs such as our grid to look at that particular option. just keeping yourself educated on what materials are in existence and what materials have been developed. And emerging contaminants are certainly one where products like Sorb Seal have been developed over 5 or 6 years to combat that. I probably haven't got 5, but probably the last and most important is buy Australian made, support Australian industries, and support Australian employees. So that's probably my final take out on this.
Thank you for that, and what a great note to finish this afternoon's webinar on. And it is all we have time for today. So please join me once again in thanking James Mackenzie and Anthony Spiteri for their time and input. I'd also like to warmly thank Engineers Australia's industry partner Geofabrics for their continuing support. As always, we're looking to improve and looking for your feedback. So if you could please just take a couple of minutes to complete a short feedback form, which is linked in the description box below, which helps us improve and plan for future sessions. Thank you again for joining us, and we hope to see you at our next Thought Leaders event. Thank you and good afternoon.